Hello, this is Dr. Baxley. Welcome to part 6 of the video lecture for Chapter 6, Thermochemistry. The topic of this video is enthalpies of formation, or how much heat energy is released when a molecule or compound forms from its elements. As always, I hope you have your printable lecture notes with you. It'll help you follow along, and you'll be able to answer some questions right in the printable lecture notes. Let's start with a definition of enthalpies of formation. The enthalpy of formation, delta HF, where the F stands for formation, is the heat energy change from when 1 mole of a compound is formed from its elements. The critical parts of the definition are the 1 mole part and the elements part. Also, the reaction has to be taking place at standard conditions, 1 atmosphere and 25 Celsius. Let's look at an example for carbon dioxide. The chemical equation that would represent the enthalpy of formation, or delta HF, would be forming 1 mole of CO2 from its elements, carbon solid and oxygen gas. In this case, you could look up the value for delta HF, and it would be negative 393.5 kilojoules for every mole of CO2 formed. Here's another example, C6H7N. It's a foul-smelling liquid. It smells kind of like fish. For this particular substance, making 1 mole of it from its elements is going to involve some fractions, because the elemental form of hydrogen is H2, and the elemental form of nitrogen is N2. So here's the chemical equation for forming 1 mole of the substance, where 6 solid carbons would have to interact with 7 halves H2, which gives 7 H's total, plus 1 half N2, which gives 1 N total, to make 1 mole of this particular substance. And one can look up the delta HF value for that particular compound also. Now, in previous chemistry problems, you would have to balance this chemical equation by getting rid of all the fractions. But in thermochemical equations, fractions are okay. The definition of delta H depends on 1 mole of the compound being formed, so in this case we have to have the fractions present. Here are a few more notes about enthalpies of formation. In the reactants portion, the most stable form of the element is always used. For example, carbon graphite is used instead of diamond, but we'll just treat carbon as solid. Other elements that would be in their stable form would be oxygen gas, or iron solid, or bromine liquid. Let's think about one of these elements, O2. We could ask ourselves, what is the delta HF equation for O2? This would be for the formation of oxygen gas in its standard state from its element. Let's check out the chemical equation. O2 gas would go to O2 gas. Is there a chemical change there for making 1 mole of O2 gas from its elements, O2 gas? There's not really a chemical change. That also means there's not a thermochemical change. I'm going to ask you to memorize all the delta HF values for all of the elements. Fortunately, since there's no chemical change in making an element in its standard state from its elements in its standard state, all of the delta HF values are equal to 0. So I'm making you memorize 0. 0 is nothing. So I'm making you memorize nothing, which not many teachers will tell you to do. Where are you going to find those enthalpies of formation? Well, there's a table in chapter 6 of your text that has a limited number of delta HF values, or enthalpies of formation, for certain substances. There's also a much more detailed appendix. It's Appendix D in the back of your book. Let's just take a look at this table quickly. You can see that bromine liquid is here. That's the elemental form of bromine, and it has 0 for its delta HF. A little bit lower on the table, we can see that methanol, CH3OH, has a value in the table in chapter 6 of negative 238.6 kilojoules per mole. But in Appendix D, you'll see a value for methane in the gas phase that has a slightly lower delta HF. Make sure you keep in mind the states of matter, because just like in Hess's law, states of matter matter. We can use delta HF values to calculate enthalpies of a reaction. Now in this class so far, we've learned 2 ways of calculating delta H for a reaction. We've looked at one way, that was calorimetry. We've looked at a second method, which was Hess's law, but this is going to be the 3rd way we know of to calculate enthalpies of reaction, using the delta HF values. In order to calculate delta H, one can take the sum of the delta HF values of the products and subtract from it the sum of the delta HF values of the reactants, and that will give you the delta H for the overall reaction. This formula can be found in the textbook, and it's a pretty crazy looking formula. It looks kind of evil to me with all these sharp angles, but it's really not that bad if you break it down into simpler parts. This crazy Greek letter, sigma, just stands for sum. The N react part just stands for the number of moles in the coefficient. And then of course there's the delta HF values. I've got a kinder, gentler formula here that shows the delta H of the reaction is equal to the sum of the delta HF of the products times their coefficients, minus, and I use a comically large negative sign, in comically large square brackets, the sum of the delta HF values of the reactants times their coefficients. Now all of this works because of Hess's law that says that the overall delta H of a reaction is equal to the sum of the delta H values of individual parts that add up to that overall reaction. We'll look at how this formula relates to Hess's law towards the end of the video. Let's look at a sample problem, calculating the delta H for the following reaction. Now we know two ways already of calculating delta H for reactions. We know calorimetry and Hess's law. For calorimetry, you'd need some information, like delta T, and maybe specific heat capacities, and mass. We don't have any of that information for this particular problem. We also know of Hess's law, but we don't have a series of equations with a bunch of delta H values. We're going to have to figure out another way to solve this problem, and that's using the delta HF values for each of the different reactants and products. Normally, you'd have to look these values up in Appendix D of the text, but I've got them here for you. If you're feeling confident, you could try to calculate the answer yourself. It's at the bottom of the screen. Otherwise, I'll walk you through the solution to this particular problem. We can use that same equation. The delta H of the reaction is equal to the sum of the delta HF of the products times their coefficients, minus the sum of the delta HF of the reactants times all their coefficients. Here's the whole worked out equation with all the delta HF values. Let's just look at some of the key parts to this equation. The products come first, and then subtract from those the reactants. So here is NO, which shows up in the products. Its delta HF is negative 91.3. That's kilojoules for every mole. For the HNO3, there are 2 moles of those in the coefficient, so its delta HF has to get multiplied by 2. The water molecule only has 1 mole in the coefficients in the chemical equation. It gets multiplied by 1. And then the last reactant is 3 moles of NO2, so there's 3 moles of NO2 times its delta HF. If you work out the arithmetic, the delta H of the reaction works out to be 119.7 kilojoules, and that would be negative. Since we don't know the tenths place in some of the delta HF values, this really should be 120 kilojoules negative, or 1.20 times 10 to the 2 kilojoules. And that's the delta H for the reaction. If you were writing a thermochemical equation, that could go up here. Delta H of reaction is now equal to negative 1.20 times 10 to the 2 kilojoules. And don't forget that's scaled for mole of reaction, or per mole as a coefficient of each of the substances in the equation. Here's another sample problem. Calculate the delta H for the following reaction. We can look at this, and we can think, where would we start? Well, do we have calorimetry data? Calorimetry data would be things like delta T, specific heat capacity, and masses. We don't have any of that kind of information, so we're not going to be able to use calorimetry. The other method we have for solving for the delta H for a reaction is Hess's law. But in Hess's law, we need a whole series of equations with delta H values. We don't have that information either. So the only way we're going to be able to solve for the delta H for this reaction is to use the delta HF values. You could look those values up in a table, but here they are for you. I've left out the delta HF value for oxygen gas, but I do have the answer down at the bottom of the screen. So if you'd like to try that out, see if you can get the answer, pause the video and work it out. Otherwise, I'll show you the solution. We can use the same formula for the delta H reaction that we did earlier. The sum of the delta HF of the products times their coefficients minus the sum of the delta HF of the reactants times their coefficients. If we add this all in, including the coefficients from the chemical equations, like the 2 for the SO2 or the 2 for the H2S, this would work out to be the delta H for the reaction that's given below. Here's a sample problem for the combustion of ethylene C2H4 that is exothermic. The question asks to calculate the amount of heat released when a certain amount of CO2 is formed. One thing you would need to know to answer this question would be the delta H of the reaction. There are only 3 ways to figure out the delta H of the reaction. Do you have calorimetry data? No. Do you have Hess's law data? No. So you'd have to have the data for the delta HF values for the reaction. Here they are. Again, I've left out the value for delta HF of oxygen gas, something you should have memorized by now. The answer's down there in the bottom of the screen in terms of kilojoules of energy that are released. Pause the video, see if you can work out at least the delta H of the reaction. Okay, we can calculate the delta H of the reaction via the delta HF values. The delta H of the reaction works out to be negative 1,411 kilojoules. But that's per 2 moles of CO2 forming. So these two numbers are linked together. Since the reaction only forms 4.79 grams of CO2, the number of moles of CO2 would need to be calculated via the molar mass. And then, just like in the stoichiometry of thermochemical equations that you might have seen in a previous video, the number of moles of CO2 can be multiplied by the number of kilojoules per mole of CO2 in the chemical equation. And that works out to be the 76.8 kilojoules. You might wonder why this answer is given as a positive number, while delta H is negative. Well, this is a funny thing about thermochemistry. And then if we ask a question of how much heat is released, we would answer in a positive number, 76.8 kilojoules of heat is released. However, if you're talking about the delta H of a reaction, the negative sign is important because it tells you which direction heat is going. Let's look at the delta HF equation in a little more detail for this particular reaction, where CO reacts with N2O to make CO2 and N2. And we'll figure out how this delta HF of the products minus the delta HF of the reactants works out. Let's imagine we have some reactants. Here's the CO and N2O, and those are going to turn into products in a direct reaction to make the CO2 and the N2. We could envision this as starting with elements in their standard state. And so we could start with carbon and oxygen and nitrogen as elements in their standard state. And we could use delta HF values or delta HF equations to think about those elements turning into reactants. Now, if those elements turn into reactants, we would know their delta HF values by looking them up in Appendix D. We could also think of those same elements as turning into products. Now, if we wanted to calculate the delta H value for this part of the equation, and we knew these two values, the delta H of this reaction, and then the delta H of the second reaction, we could do some simple arithmetic to subtract this portion away from the total. And so this is where the formula of delta H of reaction equals delta HF of the products minus delta HF of the reactants comes in. Because this larger part of energy, that's the delta HF of the products, how much heat energy is released or absorbed when products are made from their elements. And the smaller piece of energy is the delta HF of the reactants, how much energy is released or absorbed when the reactant molecules were formed from their elements. Since we're starting in the same place, the elements, we can subtract one value from the other, the reactants from the products, and get the value of the direct reaction itself. So that's where that equation comes from. It's all based, of course, on Hess's law, which says that an overall reaction and its delta H can be calculated from adding up disparate parts that add up to the entire equation. That's the end of the thermochemistry video series for Chapter 6.